Hello from Cambridge to wherever you are. My name is Kamessi Zhao, and I'll be talking about joint work with my PhD advisor, Professor Daniel Freund, on overbooking with bounded loss. Overbooking is the concept that companies might accept more reservations than there is room for, in anticipation of some reservations falling through. Its study has a long history in operations research dating back to the 70s. It is widely applied in many industrial settings, most prominently the airline industry, and is also one of the fundamental problems in revenue management theory. Today, we focus on introducing an algorithm with a uniform additive loss bound to a class of problems that involve overbooking, and discuss some interesting theories behind it. You might not know some of the terms I used on this slide. If you don't, no worries, they'll become clear by the end of the talk. Let me start by defining the overbooking problem, as we will treat it today. For illustrative purpose, the setup below considers an airline overbooking problem. The problem proceeds over T periods, and we're given B units of capacity. The arrivals, which you may understand as customers, come from K different types, each with a type-dependent revenue Vj and a probability Pj to show up at departure. So, with probability 1 minus Pj, a customer of type J would become a no-show at departure. This leads to the concept of overbooking, which means that we would probably accept more customers than we have capacity for, in anticipation that some of them would become no-shows. Now, in each of the T periods, we receive a potential order from customer J with probability proportional to lambda J. All of the parameters in this model are exogenously given and known. Here's an example of a possible sequence of arrivals, and we irrevocably decide at each stage whether we want to accept the customer. At departure, if the number of accepted customers who show up exceeds the capacity, we will need to pay each accepted customer who we deny boarding a compensation, which we normalize to be 1. Our objective is to maximize the sum of revenues of accepted arrivals minus compensation, and we make the decisions in an online fashion. Specifically, we're given the time horizon, the type attributes, and probabilities, but we do not know the exact sequence of arrivals, and we do not know who show up at departure. The setup presented here captures the essence of the overbooking model studied in the paper, and I have a pointer to the full paper at the end of the talk if you're interested in possible extensions that relax some of the restrictions here. For a particular sequence of arrivals vector A, suppose an algorithm produces a solution vector X, where Xj denotes how many customers of type J we have accepted in T periods. Then, the objective of the algorithm given vector A is the sum of revenue minus the expected compensation that we need to pay at departure. The expected compensation measures the expected positive difference between random variables that capture how many customers show up and the capacity B. Notice that it has a nonlinear form. The benchmark we compare ourselves to is a so-called clairvoyant optimal solution. The clairvoyant knows the exact arrival sequence of customers and thus solves the problem offline with this information of vector A. We call the objective of such clairvoyant optimal solution the clairvoyant general objective, denoted by OPT. Notice that the clairvoyant does not know who show up at departure, otherwise the benchmark would be too strong to match. Here's an example of how the solution of an online algorithm can be different from that of the offline benchmark, where we use red for acceptance and blue for rejection. The different solutions lead to different objective values. Of course, we can never do better than the clairvoyant general objective with an online algorithm, but the goal is to minimize the expected difference between the clairvoyant general objective, OPT, and the objective of the algorithm, OBJ. We define this expected difference as a loss of the algorithm, and in particular, we're interested in the order of this difference as the system parameters T and B scale large. In order to compare ourselves to the existing results in the literature, it is worth mentioning some common models studied in this line of works. To start with, note that if we only have a single leg revenue management problem without no-shows, the problem can then be solved efficiently by dynamic programming. By construction, such dynamic program provides the optimal online solution in this setup. Similarly, when no-show probabilities are equal across types, there is also no curse of dimensionality when using DP, because we only need to track the total number of customers accepted. When the no-show probabilities are type-dependent, however, DP becomes intractable as its state space grows exponentially with the number of customer types. Thus, we often have to rely on heuristics and approximations in this set. We summarize prior results that provide asymptotic guarantees using 3 metrics. First of all, whether it considers an overbooking model. Secondly, whether it achieves uniform loss guarantee. And thirdly, whether it studies a network setting. Prior results in dynamic models that involve overbooking, with or without a network, mostly come without strong guarantees. In particular, the best known loss bound in the literature is provided by Dai et al., with a fluid policy that obtains an order root T loss guarantee when cancellations are allowed in addition to no-shows. Without overbooking, a uniform additive bond has been established in the literature. Berry and Banerjee introduced a technique called compensated coupling to prove order of 1 loss guarantee using their fluid-based selector algorithm. In the absence of overbooking, there has been significant progress in the past decade with various approaches to achieve all of 1 loss, leading Dai et al. To pose as an open question whether such approaches may yield similarly strong guarantees when overbooking is allowed. As you can see, the edge connecting overbooking and all of 1 has been empty so far, and this is where our results add to the literature. In order to do so, we make use of the compensated coupling technique introduced by Berry and Banerjee, which poses significant technical challenges given the nonlinear objective that overbooking causes for our setting. To summarize, this paper studies the single-leg revenue management problem with type-dependent no-shows and provides, to the best of our knowledge, the first order of 1 loss guarantee for a dynamic revenue management problem with overbooking. We present in the rest of the talk the algorithm that achieves such uniform loss guarantee, which we call the online index policy. We denote the objective of this algorithm given arrival sequence vector A as obj vector A and call it the online index objective. Let me try to describe some of the ideas that motivate this policy and lead to our all of 1 loss guarantee. The idea for an index policy comes from ordering the customer types. Intuitively, we prefer customer types with high revenue and small show-up probability, so that we could potentially obtain the revenue while allocating the capacity to someone else. This intuition is closely related to the greedy solution for the one-dimensional Kamessi problem, which sorts items by density of value. Effectively, we think of customers with revenue Vj and show-up probability Pj as items that produce revenue Vj and take up space Pj in the Kamessi. In the rest of the talk, we assume that the customer types are sorted in decreasing order of Vj over Pj, where ties are broken in favor of higher Vj. Based on this ordering, we define the index solution, which means that we accept the remaining customers in the order of type indices. That is, an index policy accepts all customers of type J before accepting any customer of type J plus 1. The other important idea in the algorithm is that we resolve the problem in each stage as new information comes in, and pretend we know the remaining arrivals. Since we know the arrival probabilities of different types of customers, we draw 1 sample path of future arrivals, denoted by vector A prime. This allows us to imitate a certainty equivalent problem. In each period, the algorithm resolves the optimization problem that maximizes the total revenue minus compensation. Assuming that the remaining arrivals follow vector A prime, the optimization problem solves for the optimal index solution, which provides the number of customers to accept from each type. Here's an illustration for the online index policy defined in our paper. In period T, we observe customer of certain type J. We draw 1 sample path vector A prime as an estimate for future arrivals and resolve the optimization problem for the optimal index solution vector X prime. In the example here, we use breadth for acceptance and full for rejection. As shown in the example, the optimal index solution accepts all customers of type 1, accepts some customers of type 2, and rejects all customers of type beyond type 2. For the new arrival of type J, if the number of customers that we plan to accept from type J exceeds a half of all the estimated future type J arrivals, we would accept the customer. Else we reject the customer. For instance, in the example here, it is clear that we would accept a customer of type 1 and would not accept a customer of type 3 or type 4 because none of these customers are accepted in the index solution. For interesting cases like type 2, we use a half of the estimated arrivals as a threshold for acceptance or rejection. For instance, Here we would accept a new customer of type 2 because x2 prime is equal to 3, which is more than half of the 5 type 2 customers in total. Now, how can we bound the resulting loss of the online index policy? On top of the clairvoyant general objective that we have established before, we make use of the hybrid clairvoyant index objective as a benchmark. Such hybrid clairvoyant follows the online index policy up to time t-1, but notes all future arrivals on and after t, and then solves for the optimal index solution in an offline fashion at t. We use h of t to denote the hybrid clairvoyant index objective. In particular, based on this definition, h of 1 is the objective of the optimal offline index solution, which we refer to as a clairvoyant index objective. Then, we can write the expected loss of the online index policy relative to the clairvoyant general objective as the expected value of OPT minus OBJ. We decompose such expected difference into two parts, with OPT minus h of 1 being part 1 and h of 1 minus OBJ being part 2. In particular, part 1 measures the loss of restricting ourselves to index policies, and part 2 measures the loss of making decisions in an online fashion. To prove the uniform loss guarantee, we will show that both part 1 and part 2 are in the order of 1. We first show that the expected difference between the clairvoyant general objective and the clairvoyant index objective is of order 1. Theorem 1 in our paper shows that the offline optimal solution, vector x star, and the offline optimal index solution, vector x prime, have uniformly bounded L1 norm. Once we have this condition satisfied, we can show by Lipschitz continuity that part 1 is also uniformly bounded. Then, to show that vector x star and vector x prime are not too far from each other, we establish a result in lemma 4 and 5 in our paper that guarantees such similarity for every pair of customer types I and j, with I smaller than j. For the general solution vector x star, we argue that there is a constant r such that either fewer than r over pi type I customers are rejected, or fewer than r over pj type j customers are accepted. Since the index solution would accept all customers of type I before accepting any customer of type j, these lemmas essentially guarantee that the index solution and the general solution are alike, except for the constant differences here. The constant ratios here are instance dependent because they depend on the pj values, but they are independent of t and b. Intuitively, we prove these lemmas by arguing that accepting r over pi type I customers is always strictly better than accepting r over pj type j customers, no matter what other customers are accepted. Then, to show that these constant differences here would not significantly alter the structure of the solutions, we make use of a result that we call delta insensitivity. This property guarantees that there exists a constant delta such that if we want to accept an additional customer of type I, we should reject no more than delta customers of type j, and vice versa. Intuitively, this can be understood as a Lipschitz constant that guarantees continuity of the optimal number to accept from type I as a function of the number accepted from type j. Again, there will be a pointer to the full paper at the end of the talk if you're interested in the details of the results. Now we show that the expected difference between the clairvoyant index objective and the online index objective is also of order 1. Here we employ the compensated coupling technique introduced by Vera and Banerjee. In theorem 2 of our paper, we express such expected difference as a telescoping sum of the loss incurred in each period. In each period, the change in the hybrid objective is in between 0 and 1. At best, the hybrid objective is not affected by the decision made, and at worst, we make a wrong acceptance or rejection, which either incurs a compensation of 1 or loses revenue of at most 1. So what we'll want to do is to bound the probability that this difference is greater than 0. Specifically, we show that there exists a t0 that is independent of the time horizon, such that for t greater than t0, the probability of the difference being larger than 0 is bounded by 1 over t squared. As a consequence, we can bound the expected loss by the sum of 1 over t squared plus t0. So what remains to be done is the probability bound. To show that we make a mistake in period t with small probability, recall that h of t minus 1 is only greater than h of t if optimum before period T is not achievable after accepting or rejecting customer of type J at T. For instance, using the same example from before, we would accept a customer of type 2 in period T based on arrival vector A prime that we draw. For this decision of acceptance to be a mistake that cannot be undone in the future, the clairvoyant index solution must reject all customers of type J on and after T. Here's an example where we would incur such a loss. Since there are so many type 1 customers in the real arrival vector A whom we would prefer over type 2 customers, the clairvoyant index solution does not accept any type 2 customers. However, for such scenarios to happen, real arrivals must be very far away from the sample that we draw. With IID arrivals, we can apply Chernoff bound to show that such difference in arrival type counts is exponentially unlikely. This completes the proof that both part 1 and part 2 of the expected loss are in the order of 1. The results I presented here can be extended in various interesting directions. We can allow the arrival types to have different resource requirements, to have type-dependent refunds for no-show, and we can allow arrivals to be non-IID, as long as some concentration results are provided. There are also some possible extensions that remain open. The most obvious among those would be to extend our results to a network problem with no-shows. Next, it would be interesting to extend our results to capture type-dependent compensation amounts. Thirdly, since the uniform loss bound that we derived does depend on 1 over Pj, it is instance dependent. Though from a practical side, it is unlikely for 1 over Pj to be arbitrarily small. From a theoretical point of view, this leaves some room for extension. Finally, the most interesting but also the most difficult extension would be to settings where there are cancellations in addition to no-shows. To summarize, in this work, we derive order of 1 loss online algorithm for quantity-based single-resource revenue management problem with no-shows, which, to our knowledge, is the first uniform loss bound in such setting. If you're interested, the full paper can be found on SSRN. Thanks for attending the talk.